Hey everyone, we're going to move on to the next topic, which is about circular motion. So before we talked about 2D kinematics, now we're kind of going into the 2D forces, where we're going to have objects moving in circles, as you could probably guess. Now, one thing to keep in mind is that there are some things in this topic that seem a bit counterintuitive. Um, so the first thing that we want to talk about is the fact that this an object that is moving in a circular motion, we're going to actually talk in particular a uniform circular motion, which refers to an object moving at constant speed in that circular motion. Now, one thing I want to ask is, would an object be moving that's moving in circular motion, in uniform circular motion at constant speed, be in equilibrium? And the answer is no. Remember, the definition for being in equilibrium is that the velocity is constant, which means that the direction of the speed also has to remain constant as well. So an object that is moving in uniform circular motion is accelerating. In fact, an object moving in any type of circular motion is accelerating always. This is actually a very big trick question that they love throwing in there because they love saying constant speed circular motion and making you think constant speed equals equilibrium when you're supposed to know that's not true. It is constant velocity equals equilibrium. So what is the direction of the acceleration? Now, there is a way to figure this out through vector notation, where you kind of go through the whole finding the resultants with v1 and v2 at two different points. However, you do have to be careful because technically to find the acceleration, you have to subtract vectors. Now, we haven't actually talked about that. You don't really need to worry too much about it. One thing that you want to notice is that the velocity is always tangent to the circle, and the reason for this is because Newton's first law. Remember, an object in motion tends to stay in motion, moving in a straight line. This is the path the object takes, and at any point, if we stop having it go in that circular motion, if we get rid of whatever is causing it to move in that circular motion, the object will, by Newton's first law, continue moving in a straight line. So the velocity is always going to act tangent to whatever its path it's taking. It's just that in a circle, it is more important to be aware of that. Now, you don't need to worry about this too much. Basically, the idea is that if you want to subtract vectors, you basically take the negative of one of them, flip it, and then you can add those vectors. But what's important is the fact that the acceleration actually always acts perpendicular to the velocity. The velocity acts tangent, the acceleration is perpendicular, and always pointed towards the circle. Because of the fact that it's always pointing towards the circle, we call this centripetal acceleration in the form of center seeking. So centripetal actually means center seeking or towards the center. So centripetal acceleration is always perpendicular to the velocity and towards the center. The fact that it's perpendicular is how we change the direction of the velocity. We've already talked about how we can change the magnitude of the speed, the magnitude of the velocity, by either having the acceleration in the direction or in the opposite direction in order to increase or decrease that speed. Now we've added in another component to that where if it's acting perpendicular to the velocity, it will change directions. All right, so the equation that we have for the centripetal acceleration is given by this equation. AC equals v squared over r. AC is our centripetal acceleration. V is our velocity as it goes around the circle, or I should say its speed as it goes around the circle, and r is the radius from the center of the circle. Now, a lot of times we're not actually given the speed. There's many times where they instead tell us the period, since that's a much easier measurement to make. It's very hard for us to determine the speed of, let's say, Jupiter as it goes around its circular path, but we do know what the period is as it goes around the circular path. We can kind of determine that through different means. The period, if you don't remember from previous courses, is that the time it takes for the object to make one full circle or revolution around. So how can we find how can we use this period to find the speed? Well, by definition, the period is the time it takes to go once around the circle. We can use velocity equals distance over time because remember we're talking about uniform circular motion, which means that the velocity is constant and the speed is constant. So we can use the average speed equation. And what we do is we take the distance to be the circumference of the circle, or 2 pi r, and divide that by the period. So if we use this equation in conjunction with the v squared over r equation, we can use the period to find the acceleration. This equation is not given on the reference table. This is something you should know because this is part of the average speed equation. The centripetal acceleration equation is given on the reference table. So keep that in mind that this is not given. This is something that you kind of have to derive, right? So here's the first question. Pause the video, work stuff, and we'll go over in a second. All right. So they give us some numbers and they want the acceleration. So we use the velocity and the distance, plug it in, and we get 18 meters per second squared. Notice the mass is a complete red herring. You do not need that mass. All right. And here's the next question. Pause the video, work itself, and we'll go over in a second. All right. Now, notice that they give us 2 revolutions per second and the radius. We have to be very careful with this. For the most part, we want to keep our answer for the acceleration in terms of meters per second squared. So we kind of have to find a way to rewrite this. So if we go back to our equation, because this is kind of relating to the period, the velocity is going to be 2 pi r divided by the period. We do 2 revolutions, so the circumference of the circle is 2 pi r, and we do that in every second. So 2 circumferences around the circle in 1 second. That's kind of how this is being written. There are other ways you can kind of convert this, but this is kind of the easier way of going back to figuring out like what is the distance for a revolution, how many times you're going around, and things like that. So our speed as it goes around the circle is going to be 25.13 meters per second. Then I can plug that into the acceleration equation, and I end up getting our centripetal acceleration to be 316 meters per second squared. Here's the next one. Pause the video, work yourself. I'll go in a second. All right, so just trying to show you a variety of different ways that they can ask these acceleration questions, where it's not all just here's the velocity, here's the radius. Here, once again, they give us the radius, but they tell us that it makes 10 full circles in 5.3 seconds. So again, we're going to use that velocity equation first, where we do 2 pi r times the 0.53. So what we did was we took the time and we divided it by 10, because if it did 10 cycles in 5.3, then every circle took 0.53. What you could have also done was use this time, but taken the circumference and multiply it by 10, since it goes around the circle 10 times. But either way, you should have gotten that the speed was 11.86, and when you plug that into the centripetal acceleration, you get 140 meters per second squared. All right. And that was it for the centripetal acceleration. The next one is how do we find this centripetal force? Now, the net force acting on an object when it's moving in a circle is what we call the centripetal force. And just like the acceleration, it points towards the center. Remember, because we talked about how the net force always goes in the same direction as acceleration. Now, there is a very big warning that's extremely important. We've been talking about all these forces as being separate forces. You know, we have the normal force, the gravitational force, and the frictional force, and all these other forces that combine in order to give us the net force. It is important to note that the centripetal force itself is not a separate force. It's not a additional force that the object experiences. Instead, it is the net force acting on the object that is causing it to move in a circular motion. So a lot of times what you end up having is some forces will sometimes act as a centripetal force. A lot of times, you know, if you have an object spinning in a circle and it's connected by a string, well, that string is causing it to move in a circle. So that string is acting as a centripetal force, and and that tension force is acting as the centripetal force. So you would say, okay, they're looking for the centripetal force, they're actually looking for the tension force, and then you could go on and continue with your calculations. However, that's kind of the way that the regions works. The regions works where one force acts as centripetal. So a lot of times if they ask for the frictional force, you have to recognize that the friction is what's keeping it moving in the circle, and that's referring to the centripetal force. The AP, on the other hand, will have it where there will be 2 forces in the plane that are causing it to move in a circle, and you have to recognize that it's the net of those 2 forces that's equal to centripetal. Basically, the key thing is you go back to the basics of forces, where you do the FBD, you do your sum of the forces, and then when you do that part, you just have to recognize that because it's moving in a circle, that the acceleration in that equation is the centripetal acceleration. Um, so here's a perfect example. So pause video, work self, and we'll go over in a second. All right, we have four scenarios, and we need to figure out what force is acting as a centripetal force. Some of these are slightly more complicated than others, but for basis, in this case, because the wall is what's keeping them in a circle, the normal force is what's acting as a centripetal force. Here, the string is what's keeping them in the circle, so it's tension force. The moon is being held in place by gravity. Without it, it would not be moving in the circle. Is the centripetal force, and here it is friction that is causing the car to continue moving. All right. Uh, Now, the equation that we have for the centripetal force is actually just the net force equation. This is what's normally given on the reference table, Fc equals mac, because again, the centripetal force is just a net force where the acceleration is the centripetal acceleration. It's nothing crazy, but it's very common that what we're going to do is we're going to be given that velocity and then looking for the centripetal force. So we want to kind of jump the shark. We don't want to have to do two steps where we find the centripetal acceleration and then find the centripetal force. So a lot of times we like to combine the two equations into one. So very often you're going to see me kind of go to Fc equals mv squared over r. Just be aware that equation is not given on the reference table. It is just plugging v squared over r for the centripetal acceleration. That's it. Now, one thing I want to point out is there's no such thing as the centrifugal force. A lot of times, because objects, when you spin them in a circle, they seem like they want to be pushed outwards. A lot of people actually believe that there was a centrifugal force, the effect of being pulled outwards, but that's not actually what's happening. It really is just the objects trying to continue their Newtonian um, forward motion, and the object's just kind of pushing up against it. It just kind of depends on our reference frame. It's kind of like the idea how, when you're in an elevator, it feels like you're being pushed down, but that there is no pushing down force. It's really just the bottom actually accelerating you upwards. So it's an interesting, like I said, it's counterintuitive almost. All right. And like I said, what's really important, at least for the AP, is the fact that keeping in mind that the centripetal force is this net force in the plane of the circular motion. So, for example, a lot of time in this specific case, what we would do is, we would do our FBD, we break it up into its components, and if we look at this, this is the force that is acting in the plane of the circle. The circle is horizontal. So we look at the horizontal forces that are resulting in this circular motion. So what we would say is FTX, this specific horizontal component of the tension, is producing this net centripetal force. All right. So we would do the same thing. Like I said, some of the forces in the y direction would be equal to 0 because there's no acceleration vertically. And the sum of the forces in the x direction will still be equal to ma. It's just that a in that case will be given a centripetal subscript. All right, so here's a first question. Pause the video, work self, and we'll go over in a second. All right, so they give us the maximum strength that it can experience, and we want to know what the maximum speed is. So again, we could jump straight to the Fc equals mv squared over r. In this case, notice that it's saying that this is the maximum tension that it can experience. But again, the tension is what's keeping it in the circle, so the tension is the net force, net centripetal force. So this is going to be 200 equal to all this. We got to make sure that we convert the 80 centimeters into meters, and we get that the max velocity is 4 meters per second. All right, here's the next one. Pause the video, work yourself, and we'll go over in a second. All right. They want the centripetal force acting on them, so this time they actually just say it. Note that it doesn't always say this, but so I can ask the later part. So again, we do Fc equals mv squared r. We have the 800 newton, not the 800, but the 800 newtons gives us the mass. We have the speed, we have the radius. So plug all the numbers in, and we get 400 newtons. Now the next question, which is the reason why I didn't, I specified the centripetal force rather than the force acting centripetally, is I want to ask this one. So what force actually provides this centripetal force? Well, it is the frictional force. The way to think about it is what force is actually acting on him that without it, he wouldn't be moving in a circle. And if you think about it, if the athlete was running in a circle and slipped on some ice, it would not continue in that circle, but actually slip outside of the circle. So the frictional force is necessary to keep the athlete in the circle. And what would happen if the radius suddenly decreased? Well, the force needed to keep him in this circular motion would exceed the frictional force, causing him to slip out of the circle. Remember, the frictional force has a maximum force that can be provided to it before it gives out. And remember, as we've talked about, the frictional force in this case is the sliding force. Without that, this object is actually experiencing a static force. So that static has that maximum, and if we go beyond that static force, it will cause it to slip and stop being in the circle, which is why it's so dangerous to make very sharp turns at very fast speeds when you have things like wet or icy roads, because those have a lot lower frictional forces and therefore cannot handle as high of turns as you would normally do. This is the last one, so pause the video, work itself. I'm going to go over a second. All right. So given the numbers, we want to find the centrifugal acceleration. We just plug and chug. Again, 30 and 20 goes into the equation, and we get 45 meters per second squared. Follow up, what is the direction? What point represents the centripetal force? Well, the centripetal force always points towards the center, so it's going to be towards C. And the following question, what if the string breaks, what direction will the plane move? So this is just another way of asking what's the direction of the velocity. The velocity is always tangent to the circle, so it's going to move in a straight line towards B. And that's it. If you have any follow-up questions, feel free to let me know. We'll do some more of the practice questions in class. If you have any questions, feel free to let me know. Good luck and have a great day.